Okay, here we go. So this is problem 420. And let's just review quickly that we want to write two equations for shear force and bending moment. One that's going to be valid from 0 to L over 2. You can see the loading is constant. And then from L over 2 to L, where a second kind of load shape is in there. So let's, I'll put my pin down here, somewhere between 0 L over 2. Would you want to work the left side or the right side? Yeah, the loading is a lot easier on the left side, but it requires that we get the shear and moment. So we'll have to do that. So let's talk about the second one where we go here, somewhere between L over 2 and L. And now do you want to look at the left side or the right side? I think the right side is going to be a lot easier. The left side would be really tedious because you'd have a rectangular section from 0 to L over 2, and then you have this little trapezoidal section. So there'd be a lot of intricate and tedious distances to find, and also you'd have to deal with 3 concentrated equivalent forces. So the right side would be easier, I think. So if that is our kind of strategy, let's go ahead and start. So I'll draw a free body diagram of the structure and assume on the left side that I have a positive shear force and a positive bending moment. And I'm going to replace the distributed load, which is constant over the first half and then triangular over the second half. And what is that value? It's W naught. Okay, so I'm going to replace that first section with a concentrated force. And what is that value? What's the area of the rectangle, which is W naught L over 2. So W naught L over 2. And I'll probably sum moments about A. So what's the distance to that point? Right, it's the total distance divided by 2, so that'll be L over 4. And then I'll have the concentrated equivalent of the triangular section, which is 1/2 the base, L over 2 times the height, and you can see I get W naught L over 4, and what's the distance to there? Well, I know the first part is L over 2, then what's this part here? 1/3. 1/3 of that. So I've got L over 2 plus 1/3 of L over 2. So it looks like I got L over 2 plus L over 6. L over 2 is 3/6 plus a 6 is 4/6. So that's what? 2L over 3? Did I do that right?
Yes.
Okay. With all that, now I can proceed to do the reaction. So let's assume right-hand rule, and we'll sum moments about A. So at A, my unknown moment is a positive bending moment. When I'm summing moments using my right-hand rule sign convention, this is a negative moment. All these forces also create negative. So the first force will be W naught L over 2, and its moment arm is L over 4, minus the triangular section, which is W naught L over 4, times its moment arm, which is 2L over 3. So the moment is going to be negative, and let's see, what is all this going to be? So this first one is W naught L squared over 8. minus W naught L squared over 6, right? This 2 cancels here, and I get a 2 in the denominator, 2 times 6. You guys buying that so far? So common denominator for this would be what? 24? So this would be 3 24ths plus 4 24ths, so I get negative 7 W naught L squared over 24. Does that sound right?
Yes.
Does that sound familiar?
Yes.
Oh, good. Anybody else? Sound okay? Who asked for this problem? Everybody. Okay, so you can see these symbolic problems can be a little tricky. You just have to work your way through them slowly. So now we sum forces. We have the shear acting up minus the rectangular portion of the load, which is W naught L over 2, minus the triangular portion, W naught L over 4. So it looks like the shear is going to be equal to, well, that's a half and a quarter. That's just 3/4, right? So it's 3 W naught L over 4. Okay, so now we can proceed to try to do the first section. So we're going to look at equations that are between 0 and L over 2. So now when I draw my free body diagram of that section, all right, I know on the left side now I have a negative bending moment, which goes in this direction, has a value of 7 W naught L squared over 24. And I have a positive shear, which goes up, of 3 W naught L over 4. And then I have my distributed load over the section. It's constant at W naught, and this section is length X. And then I have my positive shear in positive bending moment. You guys see anything that we're missing for the first section? Okay, I can come back now on this this distributed load and get a concentrated equivalent force, which would be the area of the curve. It's constant, so it's just a rectangle. So the area of the rectangle is base x times height. So you get W naught x, and the distance from the cut is half the total distance of the segment. The segment is x, so this should be x over 2. Okay? I'm going to draw a line to kind of break that up so it won't look like it's all jammed together. So now I'll come over here and we will sum moments about our cut. Make sure we're in equilibrium. Again, choosing right-hand rule for my sign convention. Let me slide it up a little bit. So I'll start here. The moment at the cut, I have the moment I'm looking for, M, and that creates positive moment. The concentrated equivalent force creates what? Positive or negative? Positive. So it's a force of W naught x with a moment arm of x over 2, right? Then I have the shear force creating what kind of moment? Negative. So the value of that is 3 W naught L over 4. And what's its moment arm? X. And then I have the moment down here at the end, which is positive or negative? It's positive with my sign convention, right? Right-hand rule. So it'll be plus 7 W naught L squared over 24. So now I just collect all my terms and solve for the moment. So let's see, I'll try to find the largest term first. Here's an x squared term. So I'll say that's going to be negative W naught x squared over 2 plus 3 W naught LX over 4 minus 7 W naught L squared over 24. Yeah, that looks good. Now, notice the dimension of each term. Each term has a W naught, and then each term has x squared is length squared, LX is length squared, and L squared is length squared. So all the terms look compatible, so they should be able to sum up. At this point, you could leave it like this. I'm sure the author has figured out some clever way of factoring some things out to make it look pretty. But you could just leave it like that. Right now, the only thing we can check is that we know the moment at x equals 0 should be equal to what we found here, and we solve for it as negative 7 W naught L squared over 24. And if you put in x equals 0 here, our equation gives you that. So it seems to match right now what we have. The last little bit we can do here would be to sum the forces in the y direction. So looking at our free body diagram, we have shear, and it's acting down, so that's negative. Our applied force is acting down, W naught x. And then our shear force on the left side, our reaction shear, is up. 3 W naught L over 4. So it looks like our shear, as a function of x, is going to be equal to minus W naught x plus 3 W naught L over 4. Now, one thing we know, we've already proven that the derivative of the moment should equal the shear. And is that true? Let's look at our moment equation. If you take the derivative of this with respect to x, that seems to work. Everybody see that? So that's cool. And the other thing that we know is that our shear equation at x equals 0 better give us a positive shear of 3 W naught L over 4, and if you put x equals 0 in, you get that. So that's all we can really check right now. So it seems like everything's progressing pretty good. So what do we do next? We have to now go and look from L over 2 to L. So I'll just kind of cover that up. And we'll now say we want to go from L over 2 to L. So now I'm going to cut the structure between L over 2 to L. We've talked about it earlier, but just remind you that we're going to look with the right-hand side now. So I'm going to draw that section of the structure to the right of the cut. So that means that I'm going to measure over to that side, and that will be x. So what will be the length of the cut that I'm making? It'll be the total length, which is L, minus x. And then I have this guy. We're going to have to do some work here to find what that is. We do know that we have, at the cut, positive shear positive bending moment. And of course, with the triangle, we'll figure out what that force is. And of course, what the distance is. So this looks like a simple free body, but you see one of the challenges is we have to write this function in x.
That's what
so
would be my length.
How do you do that?
1/3 of L minus x.
Well, you know the slope,
Right.
So let's look at the general equation for the line. ax plus b, right?
Yes, sir.
We know that a is the slope. And what is the slope of that line? Well, it's going to be rise over run. So it's going to drop W naught over a length of L over 2. Right?
Yes, sir.
So what is that? That's minus 2 W naught over L. So there's my slope. So what's B?
Can we cut this at like the place that's like, remember how you said you can cut it pretty much at the same line? Just on one side of the one side. L over 2, why can't we just cut it?
We're not cutting it L over 2. We're cutting it anywhere we want between L over 2 and L.
I understand, so why can't we cut it as close to the midpoint and say it is the midpoint? Do you know?
Well, if you cut it at the midpoint, you're getting the shear moment at the midpoint, not as a variable.
Okay, I understand, yeah. Sorry.
So that's why we're doing everything in terms of the variable x. So this is really the challenge of this problem, is how do you come up with this little equation? So what is the y-intercept? Well, remember the way we're doing x, since x starts from here, that intercept would be to project this line all the way back to x equals 0. And what would that be? Well, similar triangles tell you if it's W naught at half the distance, it'll be 2 W naught at the whole distance. So this ought to be 2 W naught. So now the load as a function of x becomes, let's see, would be minus 2 W naught over L x plus 2 W naught. Now, it might be easier for us to rewrite this a little bit. That 2 W naught's in both of them, so let's pull that out. And I'm left with 1 minus x over L. Right? So check it. When x is 0, what do you get? 2 W naught. When x is equal to L, what do you get? 0. When x is equal to L over 2, you get a half. Cancels the 2, you get W naught. So that gives me the value of the intensity of the load anywhere along that line. Of course, we only want it from L over 2 to L.
How did you get B again?
It's the intercept, right? So I'm trying to write an equation for this line, so I project its slope all the way back to where the intercept is, where x is 0. So see, I kind of drew this little triangle. So now the big triangle is L to whatever this is, ought to be the same as L over 2 to W naught. So since we double the distance, we double the height. It's just going to make our calculations a little messy. Because now you can see our force, right, is going to be 1/2 the base. What's the base? L minus x. And then what's the height? It's all that stuff. 2 W naught, 1 minus x over L. Not pretty looking, but that's what it is. And what's D? It's 1/3 of this distance, so it's L minus x divided by 3. So at this point, you just have to shove all that stuff in there and solve for it. You're going to get just a long set of terms, and we may just want to leave them like they are. So now if I sum moments about the cut and set them, make sure they're in equilibrium, let's see what we have. So starting here, this moment is negative. I only have one force, right? F. And it's creating what kind of moment? Negative. So F is, I'll put it in brackets. It's, first of all, let's see, the half and the 2 cancel, right? So I just get W naught L minus X 1 minus X over L, right? And then times D, which is L minus X over 3. So remember, this is the force, this is the distance. That's it. So solve for the moment. So the moment as a function of X will just be all of that stuff. So I'm going to leave the minus sign right where it is. I'll leave it there. There's an L over X, or L minus X. There's an L minus X. So I'll bring the 1/3 in. So I've got W naught over 3 L minus X squared times 1 minus X over L. Here's your moment equation. You just leave it like that. You don't have to expand it. What's the moment at X equal L? Well, it's the free end. So what's the moment at the free end? 0. Does our equation give us 0 at X equal L? Well, when X is equal to L, that's 0. So it seems to work. Now what would be really cool, which I don't think we have time to do today, but you could, is you could go back to this equation, which is the moment, plug in X L over 2, plug in L over 2 here, and those should give you the same value. I won't do that today, but you could do that. Go ahead to finish this problem up. Let's go ahead and sum the forces in the y direction. So according to our free body, the shear is acting up and our force is acting down. Here's our force, which was W naught L minus X. 1 minus X over L. That's a 1, by the way. So the shear would be W naught X L minus X 1 minus X over L. What's the shear at the free end? Oh, you can't see it, sorry. What's the shear at the free end? 0. Does our equation give us that? Should be 0. And what is it? Put in X equal L, 0. The same thing could be said about matching this equation at X equal L over 2 with our previous equation at L over 2. They should give you probably the same value. Is this the derivative of that? A little more challenging to do, but you can see I think the first term matches nicely. Does it? I lost my 3. Did I lose my 3? No, I didn't lose my 3. I guess you'll have to look at it carefully because this is, you'd have to expand this out. You're going to end up with an x cubed term in there, right? So when you take that derivative, you'll get a 3, and that 3 will cancel this 3. All the other terms. There's probably some nice little rule you could do to apply, but I'm just going to say that, yeah, But I'm not gonna do it.
That's what we do. Sure,
We're just like, sure.
close enough.
This is definitely a homework problem.
Please tell us you won't get
This would not be an exam problem. We've just spent
the whole class.
almost half an hour on this problem. This is not a problem that you could be given on the exam. Now, what would have made this problem a lot easier to handle is if we'd have had numbers for L and W0. It would have made the problem process a lot faster. Okay. Any other questions before I shut this down? None? Did anybody get this, by the way, for homework?
I got all the way up to that, and then I couldn't figure that part out.
Oh, okay. All right. Well, I'll go ahead and stop this then.